All right, I'd like to combine the two laws that we did first, the Charles Law and Boyle's Law, and they can be put together into what's called the combined gas law. Some people jokingly call it Choyle's Law, obviously a combo of Charles and Boyle's. But this can be used to determine how changing two variables at a time will affect the third variable. Here's just an illustration. Of course, if I expand the volume, the number of collisions goes down in this container, and then the pressure drops. And then you can also, of course, factor in temperature. So what I've done here is combined the two laws. If I gave you a problem and told you the temperature remains constant, well, that would mean this number and this number would be the same. So in math, of course, we could cancel them, and I'm left with P1 V1 is equal to P2 V2. Well, that's the first law we did, Boyle's Law. If I told you the pressure doesn't change and the pressure is constant, well, again, this number and this number would be the same. So again, they would cancel, and I'd be left with V1 over T1 is equal to V2 over T2. So again, you get Charles' law. So both Charles and Boyle's laws are combined here. But when I put them together like this, I can combine and solve for multiple variables. So for instance, a gas occupies a volume of 72 milliliters at 25 degrees C on 198 kilopascals. Convert these to standard conditions. So again, what would the 72 milliliters be if I was at 0 degrees C and again 101.325 kilopascals, which is standard pressure? So again, let's just kind of go through that. So what is my initial pressure? 198 kPas. What's my initial volume? 72 milliliters. What's my initial temperature? Remember, temperatures for all of these problems must be in Kelvin, so that's going to be 298. The new pressure is going to be 101.325. That's your standard pressure in kilopascals. Again, make sure your units match. If my original pressure was in millimeters of mercury, then I'd put 760 here. If it was in atmospheres, I'd put 1, and so forth. I'm trying to find V2. And T2, again, is standard temperature, which is 273 degrees Kelvin or 0 degrees C. So now what I would do is fill in my numbers. There's my P1, V1, and T1 on the left, my P2 and T2 on the right, and I'm solving for V2. Now again, just to review your algebra, what I can do then is to get rid of that 273, I would cross multiply that up, so that will be in the numerator on my left side. I would divide both sides by the 101.325, so that'll appear on the bottom on the left. So there's that 273 up top. Notice the 273 on the bottom cancels out, or the Kelvin, I'm sorry, should cancel out. And again, there's my 101.325. And again, notice that my kPa, the units there, will cancel out. So now basically I'm going to take the 273 times 198 times 72 and divide that by the product of 101.325 times 298, and I get a final answer of 129 milliliters. So again, it's very similar to just the Charles and the Boyles. You pull out the original conditions, fill them in, and do the math.